If you compress the entire 13.8 billion-year history of the cosmos into a single 13-hour film, stars would blink on and off like flickering bulbs, and the entirety of human existence would pass so fast it would barely register to us. Time feels relentless and smooth. Every living thing on Earth organizes its entire existence around this forward flow, stockpiling resources and fighting to survive long enough to push the next generation into the future. In classical physics, this macroscopic experience seems to hold up. Einstein's relativity weaves time directly into the physical fabric of reality, treating it as an inseparable dimension alongside space, mass, and the speed of light. But zoom in close enough, and that fabric unravels. Down at the quantum level, time becomes a complete outsider. It sits on the periphery, having absolutely no direct influence on the base state of a particle. The physicist Wolfgang Pauli pointed out a glaring mathematical contradiction. If time were a standard quantum operator, something that actually interacted with particles to change their state, the universe would require infinite negative energy to function. Since even a completely empty vacuum contains baseline positive energy, this infinite negative state cannot exist. That leaves us with a difficult truth. Because time lacks the physical mechanisms to alter quantum states, our everyday experience of a constantly ticking timeline is an illusion, one that doesn't actually operate in the basement of reality. In quantum mechanics, everything exists as a fuzzy cloud of probability. To determine a particle's actual position, you have to hit it with a physical action, and operator erecting a physical barrier or measuring it forces that hazy cloud to collapse into a defined local particle. These physical measurements are strictly governed by Werner Heisenberg's uncertainty principle, limiting how much we can know at once. But time triggers no collapse, it forces no physical interaction, and it is completely immune to the rules of uncertainty. When physicists tried to force these two conflicting worlds, quantum mechanics and relativity, into a single framework, producing the Wheeler-DeWitt equation, this mathematical model describes the total energy of the entire space-time structure of the cosmos, but the answer it spit out was exactly zero. An energy value of zero means a system does not change. Stripped of our human perception, the universe is essentially a static, pre-written book. Nothing intrinsically moves forward, leaving physics without any mechanism for the clock on your wall. If the universe is a static landscape, we have to reconsider what actually defines change. We must look past the empty passage of seconds and focus on the underlying architecture of the cosmos, information. We usually treat data as an abstract concept, but physicists increasingly view it as a hard physical currency. Every interaction is recorded, and this information is strictly conserved alongside matter and energy. Think of a physical book, creating the paper, binding the pages, printing the ink, and later reading those words. Every single step requires a tangible expenditure of cosmic energy. The simple act of storing facts has a physical cost. In 2010, the physicist Eric Verlinde took this concept and proposed a hypothesis known as entropic gravity. This animated diagram illustrates Verlinde's core logic. A single, isolated atom has no temperature. You cannot measure whether it is hot or cold. Heat is an emergent property, a statistical average that only exists when thousands of atoms interact together. Apply that exact same logic to gravity. You cannot measure the gravitational pull of a single quantum particle. It doesn't have one. The curve only appears when billions of pieces of physical information clump together and interact. Gravity, in this model, is not a foundational force pulling objects together. It is a thermodynamic byproduct, the resulting strain of the universe processing massive amounts of physical data in one place. Every chemical reaction, every stellar explosion, and every collision is permanently logged. The cosmos writes this historical record directly into the geometric fabric of spacetime. At the quantum level, particles don't follow one path. They operate in superposition, existing in multiple potential states simultaneously, until an interaction forces an outcome out of all those possibilities. Probability dictates that only one result emerges in our physical reality, while the rest vanish. However, the energy the universe spent calculating those unchosen outcomes does not disappear. Those parallel possibilities are still recorded. They become hidden information, ghost data, constantly stacking up in the invisible background of reality, layer by layer, interaction by interaction. Because the physical universe refuses to delete anything, it acts like an ever-expanding ledger. The total amount of information and the entropy associated with keeping track of it all constantly increases, adding literal weight to reality. Scale this ledger up to a macroscopic structure like a galaxy, and you are looking at a dense, incredibly old hub representing billions of years of relentless, chaotic quantum interactions. We can easily map the visible matter, the stars, the dust, the planets, but orbiting right alongside all that physical material is an unfathomable accumulation of that hidden, unchosen quantum information. Just like a heavy book requires energy to exist, this colossal volume of hidden data carries physical weight. It accumulates and bends space-time with the exact same gravitational force as normal matter. This massive accumulation of hidden quantum data provides a new identity for dark matter. It functions as the gravitational footprint left by the universe's unchosen history. Galaxies rotate so fast they should theoretically fling themselves apart. The only thing holding them together is the immense gravitational glue provided by this unseen data load. The vast, invisible mass shaping our cosmos represents the heavy, inescapable burden of its own recorded history. So if the universe is entirely governed by the conservation and weight of data, and time isn't a force pulling us along, what exactly is the clock measuring? Time is simply the processing rate. It is the speed at which the universe is able to encode new information into space-time. Look at this diagram of a black hole. It contains a near infinite density of information. Trying to write new data into a space that crowded causes the system to lag under the heavy processing load, which is why time dilates and physically slows down the closer you get to the center. The exact same bottleneck happens when a particle accelerates toward the speed of light. Its position across the microscopic Planck grid changes so rapidly that the universe struggles to update the ledger. To keep the math intact, the system forces the traveling entity's local time to slow down. Our experience of time is the sound of the cosmic ledger being updated. Through every action and choice, we are not passing through a river, we are riding the heavy, unalterable geometric code of reality.